All right, so these notes are actually in your 2.1, the very last page of your 2.1 notes. And I said we'd come back to it if we have a chance. So I'm going to try to explain it. We'll see if it works out. So we're going to talk about the sandwich theorem. Like I said, it's a really small little thing, but it's really kind of cool. And I see that I've missed this E right here. That should say some interval. So sandwich theorem says this. If you've got three functions and that this f of x is always between g of x and h of x, for all things that aren't equal to c, for all values of x that aren't equal to c, and that if you take the limit of each of those as you go to c, and that if g of x as you go to c is L and h of x as you go to c is L, then this guy, since it's always between, it's going to have to be L too. Okay, so if this limit equals L and that equals L and f is between them all the time, then at c, it's L. That's the whole idea. So what the heck does this look like? Well, I want you to graph this guy on your calculator. All right, so it kind of looks, when I first graphed it, it kind of looked like a line. And maybe that's what it looked like. And it had some kind of bobbly boop in the middle here, and I couldn't tell what it was, so I zoomed in. If you haven't zoomed in yet, do it. Pause this video and do that. And then also zoom in several more times. When I did that, I got some crazy stuff. It's starting to look like it's wobbling all over. Remember how we said if it wobbles all over, there's maybe no limit? Well, this one's not wobbling all over and going to infinity. It's wobbling all over and looks like it's getting smaller and smaller and then bigger and bigger. So I want you to take that same graph that you've zoomed in on, and I want you to put in y2 and y3. I want you to graph these two guys, all right, and see what happens. So when I graph this, I got my one parabola, and it looks like it's always going this way, and it goes down to 0. We know it goes down to 0, okay? But then I got my bottom parabola, and it looks like it's doing the same thing, and it looks like that stuff that was wiggling around in here, it's wiggling around, and it's like doing like that. I shouldn't make it go to the bottom because it doesn't go that way, but it does go up to the top here. So it looks like it's wiggling around, like when you zoom in on here, it's wiggling around and it's getting closer and closer to this parabola, but then it's wiggling down in the middle. And we know both of those parabolas wiggle down to 0. So this function must be wiggling down to 0. That's the idea of what the squeeze theorem says. If you can squeeze it between two functions, and we squeezed it between these two functions, then you know those go to 0, well, then that guy's got to go to 0. So it says that has to be 0. Okay, that's what it looks like graphically. So I want to do the same thing. We're going to use the squeeze property to show this, guys. There's a really, really cool proof that I would love to explain to you, but I think on a video it's going to be awful. So I want you to look at your calculator and try to graph that guy. And remember, we're going to 0. And I want you to see that it's going to 1. All right, see if you can believe that, and it goes to 1. All right, I hope you graphed it. It looks pretty obvious to me, and if you zoom in and you look at your table, I think you can pretty much convince yourself that this is 1. This is one that AP tests expects you to know and love and memorize. If theta is going to 0 or x is going to 0, if it's x, sine theta over theta is 1. All right, so if I'm going to do a problem like this, by the way, we're not doing this, and this whole thing is on the handout that the substitute is supposed to give you right now. So if we're going to do that limit of sine of 3 theta over sine of 6 theta, we're going to do a little algebra and get to play around with that. So in order to do this problem, I actually want to do another problem first. So let's do the limit of sine of 3x over 3x, okay, as x goes to 0. Well, do you see that I have sine of something, we're going to call it theta over the top, divided by sine of theta. So that is 0. Okay, it is not 0, it's 1. We just got done saying it's 1. Hello, 1. That is 1, like it just says up here. Now, what if I have the limit as x goes to 0 of sine of 3x over x? Well, if I had theta over theta, it would work, right? So I have 3x inside my sign. If there was a 3 here, that would be really nice. If I had a 3 right there, it'd be really nice. So I'm going to put it in. But I can't multiply the denominator by something without multiplying the numerator by something so that they cancel back out. So if I multiply by 3 over 3, life is good. That is totally allowed. So now this part right here is 1. And that part right there is 3. So the limit is 3 times 1, or just 3. All right, so let's go back to this problem that I said we were going to do. So we're going to do this limit as x goes to 0 of sine of 3x over sine of 6x. Well, sine of 3x, I really want that to be over 3x. So, hey, let's put it over 3x. But that means we got to put 3x on the top. By the way, I need to write limit as x goes to 0. It's good to have over there. And what if I had, so this is sine of 6x. What if I had 6x on the top here? That'd be really nice. So I'll put 6x on the bottom there. That's totally allowed. All right, so we just got done saying that that's 1 over here. So now I have the limit as x goes to 0 of 3x times 1 times, now this part is also 1 because it is a reciprocal, so it's 1 over 1, which is 1. So I got 6x still on the bottom, so I'm going to put 6x on the bottom. Now if you didn't see that, if the limit of this is 1, then the limit of that guy should be 1 over 1. That's what I'm saying, because it's the reciprocal. All right, so now what do I have? Let's do some canceling. Let's see, I'm allowed to cancel factors. So now I just have 3 over 6. That's a half. Right, so the limit of this guy, it's 1/2. Now, I've got some craziness going on here, so let me move this up. I want to do that limit of 1 minus cosine over x equals 0. This one is also one that AP expects you to know, love, and memorize. So whenever you see 1 minus cosine x over x, you should be, oh, that's 0. Okay? Or if I have 1 minus cosine of 3x over 3x, 0. Done. All right, so there's a quick little proof we can do on this one. So I'm going to prove that it equals 0 by saying, all right, well, I'm going to multiply by 1 plus cosine of x over 1 plus cosine of x. Well, what happens there? I get 1, and then I get plus cosine minus cosine, and then I get minus cosine squared. So I get 1 minus cosine x plus cosine x minus, cosine squared of x. Okay, that's FOIL. On the bottom, I just have x, and I'm not going to multiply this out because I know my life is easier if I don't. So that's a cosine of x there. It's really looking bad. And I still need my limit as x goes to 0. All right, those are like terms, they're canceled. If I have 1 minus cosine with sine squared plus cosine squared equals 1, subtract the cosine of that side, 1 minus cosine squared equals sine squared. So this top is really sine squared. So I have sine squared x over x, and I really have the limit as x goes to 0, okay, and x times 1 plus cosine x. All right, I need to move this up. I've got a mess going on. So let me rewrite this. I have the limit as x goes to 0, and I said I have sine squared on top. So I'm going to take the liberty of splitting that sine squared up like that. Okay, because sine times sine. Okay, I have x on the bottom, and I have 1 plus cosine of x on the bottom. I hope you're going, woo, woo, woo. That's one of the special ones that Mom said, hello. You can call me Mom, I guess, if you want, that Miss Kate said is 1. Okay, so that one is just 1. And this, if I put in 0, well, sine of 0, I can figure that out. And cosine of 0, I can totally figure that out. So let's do it. I've got 1 times, well, sine of 0 is just 1. It is not, it's 0. Hello, sine is 0, but cosine is 1. I was ahead of myself. So I really have, well, 1 times 0 over 2, or in other words, 1 times 0, it's just 0. And that is what it asks you to prove. That is that way back up here, the limit of 1 minus cosine x over x, as x goes to 0, this is only true if x is going to 0, is just 0. So these two, this crazy one here, sine theta over theta is 1 as theta goes to 0, and 1 minus cosine x over x is 0 if x is going to 0. Those are two very special rules you need, and you're going to, on the next, on the back of this page, you're going to try some of the algebra tricks I was showing to prove and do some problems using algebra to get your limits for some of these things that involve sine and cosine. And that is like what some of you were asking me about in class. How do I do that? When it said to use my graph and then it said to prove it analytically, well, this is how you do it, kind of some of the things I'm showing. So we'll talk more about them on Monday when we get back in class, and hopefully you'll come back with just a few questions. Miss Gray has the answer key for the back with work shown, so if you get stuck and want help, please feel free to ask her for that and to use it.